not hard. Yeah, I did a grading for one student. Yeah, I got some information. Yeah, but for others, I can do pretty fast. Yeah. All right. So these 6 multiplications. Yeah. So we can easily see why 6. First, to calculate x cubed, we need 2 multiplications. Okay? Yeah. All right. Then, after that, let me use y to represent x cubed value. Yeah. Because this value we want to reuse as much as we can. Okay? Yeah. So then, this polynomial, we can rewrite it as a0, a1y, a2y squared, a3y cubed, and a4y to the 4th. Okay? Yeah. Then we can apply Horner's rule. We can apply Horner's rule. Yeah. Because in this way, we bring down the degree from 12 to 4. Yeah? So the degree from 12 to 4, much lower, the better. Yeah. So by Horner's rule, we need a 4 multiplication. Okay? Yeah. So the answer here equals 4 plus 2. Yeah. Total 6 multiplications. Yeah. All right. Yeah. That's the first question. Second answer is C. Yeah. Let me explain why not A, not B. Yeah. So here, so in a typical situation, when we use the linear search on many different input arrays, sometimes we get unordered. So most of the time we get unordered. But there are some relatively small cases we may have the ordered arrays. But when that happens, yeah, so here the question. Yeah. We will get a better efficiency whenever we process ordered array. B, we will get a better efficiency with unordered arrays. Yeah. Usually you may like to think about for A, for ordered arrays, why we cannot take advantage of it, right? Yeah. Yeah. Actually, there are some reasons you cannot take advantage of that order if you use the linear search. Yeah. So the situation is like this. When you implement linear search, you go through the array elements in the sequential order. Okay? Yeah. In that way, no matter it's ordered or unordered, you always go through the sequential order. Okay? No order change. No order change. That means you have the same efficiency for ordered or unordered. Yeah. So that's one point. Another point, yeah, the data. So for the computer programs, the computer, after it receives input data, you do not do detection, right? Ordered or unordered, you do not do detection. If you do not do detection, because if you do detection, it takes time. It takes a lot of time, okay? It may not be worth it. So you don't want to spend time on detection. Yeah. Yeah. Usually not worth it, okay? Yeah. If you do not do detection, then the computer does not know if it's ordered or unordered. Okay? Yeah. The computer does not know it. Then what's the difference? No difference. ordered or unordered. Yeah. Yeah. So here you cannot use the binary search because many of you know binary search can do much faster. Yeah. But because for binary search, we make assumption it's ordered. The data array, input array is ordered. That's our assumption. Yeah. So there, we do not do detection. Yeah. Binary search, people just assume it's ordered. Yeah. Usually people do not do detection to check if it's ordered because it's too expensive. Detection is too expensive. Okay? Yeah. So that's the reason when we do binary search, nobody does the detection. That's the reason sometimes people use it unordered data and get a wrong result. Yeah? Because no detection. When they apply binary search, you may not know you are doing wrong way. Yeah. So here, the reason we do not do detection is because it's too expensive. Here, we don't want to do detection. Okay? So we just apply linear search directly. Yeah. So no difference, ordered or unordered. Yeah. All right. Number 3, easy question. Yeah. Highest order of growth. Number 4, true. Yeah. Here, if you are familiar with this property we discussed in class, yeah, because some students, yeah, as I mentioned last time, yeah, quite some students, not in this class, in that online class, they may not watch all the videos. Yeah, they may skip some of the videos. Yeah. If they skip this video, there they answer question by their intuition. There, it's very likely they choose false. Yeah. Because the adjacent inversion, global inversion, quite different. How can you use adjacent inversion to determine if you do not have global inversion, right? Yeah. But actually we know adjacent inversion is enough to tell us, okay? Yeah. Yeah. If no adjacent inversion, that means it's sorted. If it's sorted, no global inversion. That's simple. Yeah. Number 5, is it possible one can find solution? Yeah, that's a simple yes, because we know the number of comparisons n-1, right? n-1 must be in big theta of n, right? Yeah, yeah. n-1 must be in big theta of n. So here I use the asymptotic notation a little bit. Yeah. So you can see a simple usage. Yeah. Yeah. But some students, they may not feel, yeah, because they are not familiar with asymptotic notations. Yeah. Yeah. All right. Yeah. So when I do grading, I will see, yeah, how many students do not know this asymptotic notation. Number 6, similar question. We did another one, find both maximum minimum. Yeah. You know, 3 halves times n minus, some number. Yeah. So approximately, yeah. So this one approximately 3 halves times n. Yeah. Okay. Some constant multiple of n. All right, number 7, yeah, all of them not in place, true, yeah, true, yeah, yeah. But when you answer this question, so you need to construct that particular example satisfy the condition. For the construction, that's easy. Yeah, that's very easy. Okay, all right. Yeah, all right. So here you can imagine, yeah, because some of our questions, you need to make some examples. Yeah. Sometimes it's not easy to make some examples. Yeah. Here, this one is not hard. Yeah. Here, I just show you. Yeah. All right. Yeah. Here, when I start, I can assume I have ascending order array, okay? Yeah. I have some ascending order array. Yeah. 1, 2, 3, 4, okay? Yeah. And array elements in ascending order, okay? All right. We know all of them are in place, right? Yeah, so it's not satisfied condition. Yeah. Now, can I make a shift, one position, yeah, but the last one shift to the first one, okay? Position shift, first one to second, second to third, third to fourth, and so on, okay? Yeah. One position to the right, the last one, circular shift, back to the first one. Then none of them in place, right? Yeah. Just some simple. Yeah. Do not use descending order. If you use descending order, you may have one element in the middle that is in place, right? Yeah. If you use descending order, yeah, depends on even or odd, right? If you have odd number of elements, the one in the middle is in place. Yeah. Yeah. But here, we use this kind of rotation. Yeah. One position shifting to the left or right, yeah, all out of places. Yeah. Yeah. Just construct some simple examples. Yeah. All right. Yeah, so this one, growth function, lowest order of growth, C. Yeah. Because for C, yeah, here, yeah, some students, when they feel hard to do the analysis here. Yeah. So here I may like to introduce some method to help you do a little analysis for questions like this. Yeah. So how to do that? Yeah, here. All right. So here, the relatively hard part is how to describe order of growth of log function. Order of growth. Because for the n part, is relatively easy. N part we know, the exponent. Yeah. But for log part, we cannot have any exponent number to be used as the order of growth. Yeah. Here I recommend one special way for you. Okay? So how do you describe it? Yeah. Here, we need to borrow some special method that we used in calculus. Yeah. In calculus, do you remember when you define limit, continuous function, continuity, derivative, you use some special language called epsilon delta? Epsilon delta language in calculus. We know epsilon. Epsilon in calculus, we can make it very small, very close to zero, but it's not zero, right? Arbitrarily close to zero. That's the epsilon we use in calculus. Yeah. Here, let's use epsilon the same way as we use in calculus. Yeah. All right. How to describe log m of n? We can make it approximately like n to the epsilon exponent. N to the epsilon. That epsilon could be arbitrarily small. It is smaller than any positive number. Okay, 0.0, many zero, but our epsilon still could be smaller than that. Yeah. We have this special property for epsilon. So we use n to the epsilon, But epsilon is greater than 0. We never say epsilon equals 0. Epsilon must be strictly greater than 0. Yeah? But it could be very close to 0, but never be 0. That kind of epsilon. Okay? Yeah. All right. Now, let's describe order of growth. Okay? Order of growth. Yeah. Yeah. This one, order of growth, 3/2. 3/2. Yeah. Root, square root, 1/2. 3/2. 3/2. Yeah. So that's the number. Yeah. Order of growth number. Okay. Exponential function, very large. Yeah. Because exponential, it's hard to describe. Yeah. How do you describe n to certain power? N to infinity, right? Yeah. So it's close to infinity. Yeah. You can argue. Yeah. Close to infinity. Okay. Yeah. All right. Then this one, you have 1 at the numerator, but denominator it's epsilon, right? Based on our understanding, epsilon at the denominator. So the whole thing, order of growth 1 minus epsilon, right? 1 minus epsilon. 1 minus a very small positive number. Okay, all right. Then d is 1, right? Because dominant term n, you get a 1. Okay? Minor term log n, we ignore it. Yeah. So d is 1. Now you compare all these numbers. Which one is the smallest? 1 minus epsilon. Because 1 minus epsilon is less than 1. You minus a small positive number, that's strictly less than 1. Okay? So we know C is less than D in order of growth. Yeah. In this way, we can handle log function a little better. Okay? Because we can write some formula. If you do not this way, it's hard to write any formula. Okay? Yeah. So, yeah. You can use this way. Epsilon, but that epsilon is very special. Okay? Yeah. All right. So, that's 9. Yeah. That's number 8. Number 9, if you use the same way, also good. Okay? Yeah. Let's try practice that epsilon way. Okay? All right. D, we have root of n, we have 1/2 order of growth from root. And natural log epsilon. 1/2 plus epsilon. Okay? All right. C, order of growth, this is 0.0 many 0, 1. Okay? All right. B, numerator 2, denominator 1, 2 minus 1, it's 1. Order of growth is 1. Okay? All right. A, the order of growth is epsilon. Okay? Now we compare these numbers. Epsilon 1, 0.001, and 1/2 plus epsilon. Which number is the smallest? Use our special property of epsilon. Okay? Epsilon is less than 0.00 many 0, 1. Yeah, because epsilon is less than any positive number. Okay? Less than any positive number. So the answer is A, not C. Not a C. So you can see if you use epsilon, yeah, you can do a lot of things, related to log function in a more accurate way. Yeah. All right? Yeah? Okay. Yeah. All right, so number 10, yeah, we know in the long run increases faster, exponential increases faster because this base A greater than 1. Yeah. Although it is very close to 1, but it is strictly greater than 1. Yeah. Yeah. If you use your intuition, you may feel, yeah, it's very close to 1. Yeah. But B, it's a very large monomial, yeah, huge, you know. Yeah. But in the long run, eventually, A would beat B, eventually. Yeah. Eventually. Okay? Yeah. 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 Some students, my old students, yeah, so they try to use the, graphical calculator, some online graphical calculator, try to compare. You cannot, yeah, because it's too large. If you want to see the difference, yeah, that's going forever. So you cannot get there. You cannot get there. Yeah, too far. Yeah. That's the limitation of the calculator. Okay, that's the limitation of the calculator. Yeah, so you cannot go that far. Okay, yeah, it's like going into the universe, right? Far away inside the universe. How can you go that far, right? Yeah, going to Mars, it's very far, right? Yeah, but there's even much more longer, farther than that Mars. Yeah, extremely far. Okay, so you cannot get there. But we know eventually A would beat B, yeah, just by our result in class we learned. Okay, L'Hopital's rule we learned in class. We prove it. Yeah. All right. 11, which larger? Yeah, actually B is larger. Yeah, here we can calculate it. Yeah, but many students they do not know how to calculate. They still, by their intuition, yeah, because they don't know how to calculate. By their intuition, so it looks like, A a little larger, but it's not. Yeah, here, let me do the calculation quickly. Yeah, all right. For A, log base 10 of n, that's easy, yeah, because our base is 10. So we remove the base, only keep the exponent part. That's 10 to the 10th. That's simple. Okay. You just remove the log base 10 by taking the log base 10. Okay, that's A. Yeah. B. Yeah. Now let us put 10 to the 10 to the 10 as m, then 0.00001. Okay, all right. Now, we apply some property, yeah, exponent, another exponent, yeah. 10, its exponent 10 to the 10th, yeah. Multiply 0.00001. This is actually 10 to the negative 6. Yeah. Okay? Yeah. All right. 10 to negative 6. Okay? All right. 10 to negative 6 multiply 10 to the 10. 10 minus 6, 10 to the 4. All right. Yeah. Equals 10 to the 10 to the 4th. Yeah. 10 to the 4th, that's what 10,000, right? Yeah. 10 to the 10,000. This one, the exponent 10,000. That one, exponent is 10. You can see 10,000 much larger than that 10. 10,000 exponent. The other one just 10. Okay? Yeah. Yeah. So you can see, although you see so many zero, yeah, so many, but still you can overcome all those zeros because your exponent, you have enough number of digits in power of 10, you can overcome all those zeros. Yeah. Yeah. So that's number 11. Yeah. Number 12, yeah. Only 2 true. Only 2 true. Okay? So other than 2, all the other elements out of place. Yeah. Also easy. Yeah. Also easy. How to get that? Okay. All right. Yeah. You can imagine in this way. Yeah. Yeah. Because you need to construct appropriate examples. Here, another chance you construct appropriate examples. All right. When we start 1, 2, 3, yeah, n elements ordered, right? Let's assume when we start, they are ordered, okay? All right. Then, we fix first 2. Fix first 2. Yeah. In place. When we fix them, they are in place. Okay? All right. Remaining, all the remaining, yeah. Now we do rotation. How about that? Okay? You know, 1 position shift to the right. Okay? Yeah, like that. Make them out of places. Yeah. So then, it satisfies the condition. Yeah. Yeah. So sometimes, yeah, in order to convince yourself, you may need to construct appropriate examples. Yeah. Here we did two examples. Yeah. Yeah. So then you know it is correct. Okay? Yeah. But some students, because they feel hard to construct such example, then they say not correct. Yeah. Yeah. Let me see. Yeah. I believe I can see some students doing in that way. Yeah. Because for those students, it's hard to construct such examples. Okay? Yeah. All right. I hope I have enough time. Yeah. Number 13. Yeah. 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 Number 13. Yeah. You need to spend some time to calculate. Yeah. I did it. So you need to, really do some calculation. Yeah. Yeah. So here, when I post my answer files, yeah, I have the formulas, all the formulas. So here I do not write that. Okay. Because it takes quite some time to write all the details. Yeah. So here I skip this question. Yeah. But later I will post my answer file. Okay. Yeah. Yeah. I'm typing my answers. Yeah. Yeah. I will post it soon. Yeah. All right. Number 14. Yeah. Yeah. Brute force method. Number of additions. Yeah. In my grading, so one student did, just missed by 1. Here, okay. Look at the subscript or superscript. The format, subscript, superscript, 3k plus 2. Okay. Yeah. Multiple of 3 with remainder 2. You have remainder 2. Okay, all right. Then you need to know what are the values for those k. Yeah. The first value B2, X2, K equals 0. Second one, K equals 1, 2. The last one, 110. Okay? All right. Then, when you count the number of, number of K, all right. Number of K, there are, 101, but plus sign, you need to, minus 1. Yeah. Because plus sign is 1 less than these numbers. Or you make one-to-one correspondence without looking at the first term. Okay? One-to-one correspondence. One-to-one correspondence. One-to-one correspondence. Okay? All right. So then one-to-one correspondence, you don't have the 0. Okay? You don't have the 0. Yeah. All right. Yeah. So that counting by reference. That way. Yeah. All right. Yeah. Yeah. All right. So that student did this one correct. Yeah. Not counting the first term. Yeah. All right. Number 15. Answer is 5. 5 multiplication. Do not expand. Do not expand. If you expand, you need more multiplications. Yeah. Yeah. All right. So 1 here, 1, 1. Then the parenthesis between two adjacent parenthesis pairs, 1, 1. Yeah. So total 5. Yeah. Yeah. All right. Do not expand. Yeah. All right. Yeah. So number 16. Yeah. So some formulas. Yeah. Simple formulas. Okay. Yeah. Yeah. All right. Yeah. Something like 50600. Okay. Yeah. 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 Because you need to split into some special structures. Special structures. Yeah. Yeah. In my solution, I gave the formulas. Yeah. Yeah. All right. Number 17. Yeah, this one. Yeah. Some student. Yeah. Because a few students asked me questions about this. Yeah. First, do not do expansion. Yeah. Yeah. Here, you need to take advantage of another important structure. That student, when I graded, that student didn't do this right. Yeah. Here, let me show you. First, we write this P in this way. A0 plus A1x. Yeah. We keep this part. B1x C0 plus C1x. We keep, then we take fourth power out of the product of these 3 parentheses. That's important step. Because in this way, you only need to do the fourth power only once, not 3 times. Not 3 times, okay? Only do it once. Yeah. All right. Based on the previous example, inside the bracket, we need 5 multiplications, right? But 4, 2 more. By repeated squaring, 2 more. So 5 plus 2, the answer is 7. Yeah. If you do fourth power more than once, then every time you need 2 more. Every time you need 2 more. That's not good. Okay? Yeah. So this way, take advantage of its special structure. Like this. Okay? Yeah. All right. Number 18, yeah. 2 more, yeah. Because you can compare x to the 4 with x2 first. Yeah. Binary search. Yeah, this is a simple binary search, right? Yeah. 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 Second largest. Yeah. Because when you do binary search, you need 2 comparisons. You can get a whole array sorted. If you get whole array sorted, you can easily get second largest. Okay? Yeah. So 2 more comparison. Yeah. Just use by the binary search. Yeah. Because this order tells you these 3 elements already sorted. So you can apply binary search directly. Okay? Yeah, very simple. Yeah. All right. Number 19, and let me look at how much time. Yeah. Yeah, because later, some questions, I need to do a lot of work. Yeah. Right. This one, answer is 7, not 8. Yeah. Yeah. Answer 7. Not 8. Yeah. The reason, yeah, because I noticed quite some students give 8 because you apply repeated squaring. Here, 45 multiple of 3. You have many multiple of 3 structure. Why you just use more repeated cubing? Okay, repeated cubing. Yeah. Here, let me show you how to use repeat cubing to do better. Yeah? Because you have more multiple of 3 structure. You should take advantage of that. Okay? All right. First, we do x to the 5th. X to the 5th. Right? Yeah. But x to the 5th, yeah, we do this way. Okay. X squared equals x times x. That's the first multiplication. Then x to the 4th equals x squared times x squared. That's the second multiplication. Yeah. Yeah. Then x to the 5th equals x to the 4 times x. That's third multiplication. So 3 multiplications. We get x to the 5th. Next. X to the 15th equals x to the 5th times x to the 5th times x to the 5th. 2 more multiplication. Okay? Yeah. 1, 2, 3. Yeah. Let's say 4 and 5. Okay? All right. Yeah. Then x to the 45 equals x to the 15 times x to the 15 times x to the 15. So you have number 6 and the number 7. Yeah. See? Yeah. 7. Yeah. Right. So you can see, yeah. How to take advantage of the specific structure. Is it closer to power of 3 or closer to power of 2? Here, 45 equals 5 times 9. 9 is the power of 3. Okay? So you should use repeated cubing more. Yeah, because it contains 3 square. Repeated cubing is better. Yeah. All right. Number 20. Number 20. Yeah. All right. Let me look at. Yeah. All right. So we have a lot of yeah, chat message. Let me. Yeah. Some student asked me a question. Yeah. All right. Doesn't number work for number 12 n equals 3? Yeah. Oh yeah. Oh yeah. Good question. Yeah. Good question. Yeah. All right. Yeah. That student asked me number 12. Right. Yeah. Right. That student asked, yeah, it doesn't work for n equals 3. Yeah, you're right. Yeah. N equals 3. Yeah. Good. That's the one not working. Yeah, good. Other than that, all work. So, yeah, okay, good. Yeah. So when n equals 3 not working, but n greater than 3, it works. Yeah. Okay. Yeah. So based on that, is it possible arrange only to assuming distinct? Okay, good. Yeah. Yeah. Then I should modify. Possible modify. Yeah. All right. Yeah. Then yeah. Because based on that special case, it should be false, right? Is it possible? Oh yeah. All right. Yeah. All right. So here, yeah. The question: is it possible? Yeah. These for 3 not possible. Other than 3 is 2 and 3. Yeah. 2, 3 not possible. Yeah. 2 also not possible. Okay. 2, 3 not possible. Greater than 3 possible. So based on the logic. Yeah. Yeah, let me think about it. Okay? Yeah, let me think about it. Yeah. Partially correct. Yeah. True, false. Yeah, because if we say true, it must be 100% true. If it's not 100% true, then it's not true. Okay? Yeah. So here we treat as not 100% true. Okay? Yeah. There are 2 exception cases, 2 and 3. 2 exception cases. So it's not 100% true. All right? So it's false. Yeah. It's false. Okay? If you say true, yeah, let me do this. If you say true, I give partial credit, 2 points. Yeah. Because here partially true. Okay? I give 2 points. Partial credit. Yeah. Yeah. If we say possible, let's say if we say yes, it's possible, we should make it happen, right? We should make it happen. When you say it's possible, make it happen. Okay? Yeah. Yeah. All right. Yeah. Yeah. Good. Yeah. Thank you. Yeah. That student fix this problem. Yeah. Yeah. Because here I didn't pay attention small n. I just, when I design this question, I just think about sufficiently large n. Okay? Yeah. When n is relatively large, then it's correct. Yeah. But I should be, also check the small n. Yeah. All right. Yeah. So number 20 we do in this way. Yeah. Because here there is an extra condition. X6 is not in place. That condition, usually that makes the problem a little harder. Yeah. It's quite common. In our problem solving, sometimes we have some special conditions. If we follow those conditions, then the problem relatively hard to solve. In that situation, we can do this way. First, let's ignore that condition to solve the problem. That will be much easier. Yeah. So here, our first try, we ignore the condition. Okay. Yeah. We don't worry about that. Yeah. No such condition. Okay. Yeah. Then the answer is easy, right? Yeah. The answer, the maximum number of inversions, descending order. Okay. Yeah. So if ignore, yeah. So first, we ignore the condition. Okay, yeah. Maximum number of inversions equals 1/2 times 11 times 10, right? Okay? Yeah. Any pair of elements would give us one inversion. We just count the number of pairs. Okay? All possible pairs. So this number, okay? 55. Yeah, that's 55. Yeah. And then we also know the input that corresponds to this case is array in descending order. The given array in descending order. Okay? Descending order, when the array in descending order, x6 is in place, right? x6 is in the middle. There are all the number of elements. The one in the middle is in place. Yeah. Now we go back to add this condition back. After we solve the simpler version, now we are ready to add remove the condition back to get the original question. After we add it back, we need to make x6 not in place. We need to move its position, make it not in place. Okay? All right. But when you move it, make it not in place, you will reduce the number of inversions, right? You have to reduce the number of inversions. Okay? All right. You have to reduce. When you reduce the number of inversions, the best scenario is you only reduce by 1. Because 1 is the minimum you can reduce, right? Minimum. If you do it in a wrong way, you may reduce many. Not just 1, you may reduce many. Here, we only want to reduce 1. Okay? Reduce 1. You switch x6 with its adjacent one, an adjacent element. Make a switch. An adjacent one, so you do not change inversions in other places. You only change the inversion locally. Okay? An adjacent only, you make the smallest change. Okay? Yeah. So your answer is 54. 1 fewer, because you only reduce 1. Okay? Yeah. So reduce 1 inversion by an adjacent swap with x6. Okay? Yeah. But adjacent swap with x6. Yeah. So you reduce only one inversion. Yeah. And x6 is not in place. Okay? Before the swap, that adjacent element and x6 form an inversion, but after one swap, that pair won't be an inversion anymore. So one fewer. All the other places keep the same. All other places, no change in the number of inversions. Only this swap place, it changes the inversion. Okay? Yeah. All right. That's number 20. Number 21, yeah. Given a one element array, we want to find an element neither maximum nor minimum. What is the minimum number of comparisons? Answer is 3. Yeah. So here, let me explain a little bit. Yeah. Answer. Yeah. Some students already can see it. Yeah. So here. Yeah. Here, I like to use the, problem size reduction idea. Yeah. Because when you see 100, so many students, when they see 100 elements, it's a relatively large number. So they feel hard. How do you work on 100 elements? Too many. Yeah. All right. So when you have such situation, first you change that 100 to n element array. So n sufficiently large. Okay. Yeah. Not just 1, 2. N sufficiently large. But when you change to n, you can use different numbers for n. Okay? Yeah. So you can reduce from 100. Okay? You don't have to use that many. Okay? All right. For example, you can try n equals 10. How about? Okay? Yeah. You can try n equals 10 elements. Is it possible to find an element in a 10-element array that is neither maximum nor minimum? Yeah. So you can do that. Yeah. But you may feel 10 still too many. Can you change n equals 5? Yeah. So given 5 elements, can you find some element that is neither maximum nor minimum? Yeah. Now you won't feel too hard, right? Yeah. So 5. After 5, how about 4? Okay, a little easier, a little easier. 4. One fewer, a little easier. Okay, all right. Then another reduction, 3 elements. Okay, only 3 elements. Then, because you only have 3 elements, you just sort it, okay? Yeah. So you just sort the 3 elements by 3 comparisons. Okay? And the median satisfies the condition. Okay? So for 3, you solve the problem easily. Okay? The median. 3 comparisons, yeah. Now you can go back, increase the number, yeah, because you solve the problem for n equals 3. Okay? Then you go back where n is larger than 3. Okay? Where n is larger than 3, How about you only select 3 elements from the array, okay? You do not need all of those elements. You just select arbitrary 3 elements from the given array, no matter how many. Yeah. You just need, at least the minimum number of elements in the array, 3. Okay? Yeah. So for n larger than 3, you just select arbitrary 3 elements from the array. That would work, okay? Then find the median, so that median cannot be the maximum, cannot be the minimum. Yeah, definitely here we have to assume distinct, right? Yeah, distinct elements. Yeah, otherwise, we get trouble. Yeah, we need to assume distinct. Yeah. All right. Yeah. So that's number 21. Yeah. Number 22. Yeah. Among top 9. Yeah. So here. Yeah. 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 We apply the elimination method. Yeah. Top 9. The goal. Top 9. Okay. Yeah. Do not do more comparisons than necessary. Yeah. Yeah. Because I give you a hint. Yeah. If you find the minimum, you do the comparisons more than necessary. So we can save a few more comparisons. Okay? All right, so here. Yeah. Because the top 9, okay? Top 9, that means that element eliminates all the other elements other than 9 elements. Okay? Other than 9 elements. So we need to do the calculation. 267 minus 9 equals 258. Okay? 258. That means we need to find one element that can eliminate this many elements. Then we're done. We only need one element, eliminate this many elements. Good enough. Okay? How to make one element to eliminate this many? Finding the maximum, we just need one more than this number. Okay? Yeah. So we select 259 elements from the given array. Yeah. Arbitrate 259. Okay? Yeah. So then find the maximum. Because when we find a maximum, we need this number minus 1 comparisons, right? N minus 1. Yeah. But here, N is this 259. We need 258 comparisons. And this number would work. So that would be the solution. Yeah, because this number eliminates 255 other elements. Beats that many elements. So it is better than 255 elements. So this number must be among the top. top 9. Top 9. No way to below top 9, right? There is no way this number can be below top 9. Yeah. So the answer, this answer is 258. Okay, number 22. Yeah. All right, number 23. Yeah, here. This is the hardest question. Yeah, hard. Let me see if I have enough time. Yeah, I'd better complete this one. Yeah, because it takes a long time to complete it. Yeah. All right. So now let me tell you the answer first. Yeah. Then I just work it out. Yeah. Try my best to work before the end of the class. Yeah. If not, if I cannot complete, then I would do it next time. Yeah. Answer. All right. Here, I give you a partial credit. Yeah. Yeah. Based on the answer, how close to the best answer? Okay? Yeah. The best answer. Yeah. Here, I give you these 3 cases. Yeah. Look at. So what number you get? Yeah. If you get 11 comparisons to find the solution, you get 2 points, 2 out of 4, partial credit, 2 points. All right? 2 out of 4. If you get 10 comparisons, you get a full credit. Full credit. But there is a better solution, 9 comparison. Okay? If you can get 9 comparisons, you get 4 points extra credit. Because it's hard. Okay? 4 points extra credit. So other than the original 4 points, you get 4 more points. Okay? 4 plus 4. So you can earn 8 points. How about that? If you can get this 9 comparison solution. Okay? Okay? Yeah. Let me see if I have 5 minutes. Yeah, probably enough. Okay, 5 minutes enough. I can give you the solution. Okay? All right. Yeah. When we start, let's use our finding maximum, minimum, the old one, but let's borrow first a few steps from there. Okay? Yeah. There we use when we start, we use the tournament method. Okay? 3 pairs, we do comparison. Yeah. So here I use this, the first pair x1, x2, the second pair x3, x4, the third pair x5, x6. 3 pairs. Each pair we do 1 comparison. 1, 2, 3, and we assume the upper one is greater than the lower one. Okay? Yeah. Without loss of generality. Yeah. Because, yeah. That's we call this is our round 1. Round 1. Okay? Yeah. We do this. 3 comparisons. Round 1. All right. Round 2. Now round 2. Okay? Yeah, round 2. We need to do something special, round 2. Round 2, okay? Round 2, I compare x3 and x5, okay? Yeah. These two, the larger, 2 elements, larger one, yeah, in the previous round. Yeah. There, one is larger than the other one, but no difference, right? x3 larger, x5 larger, similar situation. Yeah. So we can comfortably, assume, so that's our comparison number 4, we can assume x5 is larger. Because no difference, right? One is larger than the other, okay? No difference. We just select 1, okay? Yeah, all right. Then another comparison, then there could be difference, okay? Yeah. x2 and x4, this is the 5th comparison. Then we cannot say there is no difference, okay? x2 larger, x4 larger, the situation would be different. So we need to separate. Yeah. First case, x2 larger. Second case, x4 larger. x2 larger, I use case 1. x4 larger, I use case 2. So we need to look at each one. We need to look at each one. Okay? Yeah. All right. Look at separately. Yeah. That's round 2. Next, round 3. Round 3. Yeah. Yeah, here, yeah. Let me do next time. Yeah, here, not just the time, and I need more space. Yeah, here I run out of space. Yeah, if I write very messy. Yeah, yeah. All right. So round 3, round 4, we will finish. Okay. Yeah. If you want to try, you can try. Otherwise, so I will do the whole thing next time. Okay. So the goal, yeah. If you can get 9, you get 8 points. 4 plus 4, 4 extra credit. Yeah. 10, yeah. 11, actually, if we use our older solution, we get 11. Yeah. Because we use 7 comparison, we get a maximum minimum. Okay. After we take it out, 4 more comparison, we get next. Largest, second largest, second smallest. That's 11. If you use our older solution, you get 2 points. If we can do a little better, 1 more, 4 points, 2 more, 8 points. 8 points. That's the hardest, because that's very hard. So I give you 4 extra credit points. All right, yeah. That's it. Yeah. So I'll do it next time.